Hey, I'm Alex Renda, and I'm presenting our paper, DiffTune, Optimizing CPU Simulator Parameters with Learned Differentiable Surrogates, co-authored by Yishan Chen, Charith Mendis, and Michael Carbon. So first, let me give some background on CPU simulators. There's a massive array of different simulators, modeling all different parts of the architectural stack on all different tasks. So to narrow our scope a little bit, in this work we're going to focus specifically on basic block throughput predictors, which are CPU simulators that predict the execution time of basic blocks, which are sequences of assembly instructions with no control flow. These basic block throughput predictors are commonly used for code optimization, such as within a compiler to choose which optimizations to apply based on what the compiler thinks will result in the fastest code. Of course, these simulators don't always reliably model the actual underlying hardware, and so this is due to a combination of bugs, simplifying assumptions, and incorrect parameter settings that describe the hardware. So to address these prediction inaccuracies, in this work we present DiffTune, a method of automatically setting CPU simulator parameter values based on just coarse-grained measurements of the end-to-end behavior of the processor being modeled. DiffTune works by learning a simplified model of the simulator itself, so essentially simulating the simulator, and then optimizing the parameters of that simplified model. DiffTune's learned parameter settings allow simulators to have more accurate predictions than when using the default expert-provided parameter values. In the rest of this talk, I'll provide some more detailed background and explain precisely how DiffTune works. So let's concretize this a little bit on a specific basic block throughput predictor, LLVM-MCA. LLVM-MCA is a basic block throughput predictor included in LLVM, whose main design goal is to expose LLVM's instruction scheduling model for testing. LLVM makes two core assumptions. First, that all data writes and reads resolve in the L1 cache, so LLVM-MCA doesn't really model the memory hierarchy. And then also that code is not bottlenecked by the front end, so LLVM-MCA doesn't model fetching and decoding of instructions. LLVM-MCA models a pipeline CPU where instructions move through the pipeline based on availability of physical resources. The pipeline stages and physical resources are configured for each different target microarchitecture by parameters which describe aspects of the physical system being modeled. So operationally, you should think of these parameters as the values you'd have to set when you want to target a new microarchitecture, so say for the latest release of a new CPU. So this presentation is going to be too short to cover exactly how LLVM-MCA operates, but I'm going to do a quick skim over the parameters just to give an idea of the different kinds of parameters one would have to set to target a new microarchitecture. And the actual details of the operation of any parameters isn't super important. I'm mostly just emphasizing the complexity here. So first, in the dispatch stage, there's a dispatch width parameter that says how many instructions can be dispatched per cycle. Instructions must also reserve slots in the reorder buffer, the size of which is controlled by the reorder buffer size parameter. Instructions then wait in the issue stage until all of their dependencies are available, and so this is controlled by the write latency parameter for previous instructions minus the read advanced cycles of the instruction that is waiting. Then, in the execute stage, instructions reserve execution units for the duration specified by each instruction's port map parameter. So in sum, with the 837 instructions in our dataset, LLVM-MCA has 11,265 microarchitecture-specific parameters. And so again, each of these parameters must be set independently for each different microarchitecture that LLVM-MCA models. So the driving question behind this work is, how can we accurately set these 11,265 parameters for any given microarchitecture? One plausible approach, commonly used by LLVM-MCA's developers, is to set parameters according to their quote-unquote ground truth values, either from vendor manuals or from directly measuring the parameter values. Though there are a number of hurdles for any approach here, the biggest issue is simply this. There is not a one-to-one correspondence between measurable definitions of parameters and LLVM-MCA's semantics. For instance, LLVM-MCA defines a single write latency per instruction, but in reality, the latency actually varies depending on a number of factors, like the value of the input operand, so for instance, if you're dividing by 0 versus by some other value, it varies depending on which output operand is being read, and it can vary depending on any other sort of microarchitectural optimizations that LLVM-MCA just doesn't model. So there doesn't exist a single ground truth value for many of the parameters that must be set. It's worth noting that this is not just an issue with LLVM-MCA. This is an issue that will pop up anytime the measurement semantics don't directly correspond to the simulation semantics, which will happen pretty frequently anytime the simulator operates at a level of abstraction above that of the physical hardware, which is pretty much always. More visually, the approach looks like this. So here are LLVM-MCA's predictions for a simple basic block as we vary the value of a single parameter. So although I've drawn a dotted line connecting the points at which LLVM-MCA can actually generate predictions, LLVM-MCA doesn't have any way of taking the derivative of the timing with respect to this parameter value, and therefore it doesn't have a way of finding a value for the parameter that allows LLVM-MCA to predict something close to the true timing for this basic block. Instead, we learn a differentiable surrogate of LLVM-MCA, which is represented by this orange line. So the surrogate aims to make the same predictions as LLVM-MCA, but it is smooth and differentiable. So although the surrogate isn't precisely the same as LLVM-MCA, which you can see on the left, it's smooth and differentiable, and therefore you can use it to optimize the parameter values with gradient descent. So I want to interject and say that learning surrogates of CPU simulators is not a totally new idea. So papers from back to 2007 have actually learned surrogates of CPU simulators for design space exploration. So this is exploring the response of the simulated system to different architectural parameter settings. So while related, this prior work doesn't solve the same problem that we're solving. So not only is design space exploration a somewhat different task, but actually the exploration techniques proposed by these papers just don't scale to the massive scale task of tuning LLVM-MCA's parameters. LLVM-MCA has on the order of 10,000 lines of code, and it similarly has about 10,000 parameters that we tune. And so the exploration techniques proposed in these papers, so that's grid search and exhaustive search over parameters, just don't scale in the same way that gradient-based techniques do. All right, so back to DiffTune. At a high level, DiffTune's algorithm looks like this. First, we collect a ground truth dataset of basic blocks that exhibit the behavior that we want to model. Next, we train the differentiable surrogate, represented by f hat here, to be as similar as possible to the original simulator. We do this by iteratively sampling basic blocks from the source dataset, sampling a parameter table from some predefined parameter table sampling distribution, and then getting LLVM-MCA's prediction on that basic block when it's instantiated with the given parameter table, and then optimizing the differentiable surrogate with just standard gradient descent to mimic the behavior of the simulator. The output of the step is a differentiable surrogate such that when given an input basic block and parameter table, it can produce the same output that LLVM-MCA would produce on that basic block when instantiated with the given parameter table. Next, we train the parameter table itself. We first freeze the weights of the differentiable surrogate since it's already been trained to mimic LLVM-MCA for all input parameter tables and basic blocks. We then sample an initial parameter table estimate. Then, we iteratively sample a basic block from the original dataset, time it on the target CPU, and then pass that basic block along with the current parameter table estimate through the differentiable surrogate. And then we update the parameter table estimate by backpropagating through the differentiable surrogate to find the parameter table that the surrogate believes would lead LLVM-MCA to have the lowest error compared to the true basic block timing. Finally, we just extract the learned parameters, rounding values back to integers if necessary, and then just plug them into LLVM-MCA, and we've optimized the parameters for LLVM-MCA. So now let's talk about our implementation of DiffTune that we use for the evaluation. Up until now, the high-level algorithm that we've described has been generic for any type of simulator. However, we implement and evaluate DiffTune specifically for basic block throughput predictors. We use basic blocks from the Beehive dataset, which provides blocks and a timing methodology that conform to the assumptions made by basic block throughput predictors like LLVM-MCA. And for the differentiable surrogate, we use a modified version of Ithomol, which is a deep neural network, and therefore differentiable, that predicts the timing of x86 basic blocks. It's crucial to remember here that we're using Ithomol specifically to predict LLVM-MCA's prediction of the basic block, and not the actual ground truth timing of the basic blocks. So to apply DiffTune to a different class of simulators beyond just basic block throughput predictors, you'd first need a dataset that showcases the desired behavior, so for example full programs, and you'd also need a differentiable surrogate implementation that can accurately predict the behavior of the full simulator. So how well does DiffTune work? Well, so let me show you the error of LLVM-MCA with the default and learned parameters. Our error metric is the mean absolute percentage error, which is the absolute value of the predicted throughput minus the true throughput divided by the true throughput against the dataset from Beehive. So all we're looking at is whether the parameters lead LLVM-MCA to have low error. So here's LLVM-MCA's default error on 4 different Intel and AMD x86 microarchitectures. It's around or slightly above 25% across the board. With the parameters that DiffTune learns entirely from scratch, so entirely independently from these default parameters, we're able to not only match but actually lower the error of LLVM-MCA. In contrast, a representative search-based technique, OpenTuner, is not able to find plausible parameters at all. So we've cut off the y-axis on this chart, but OpenTuner results in error above 100% for all microarchitectures. We can apply this same technique to other basic block throughput predictors. Here are the results when we apply the exact same technique to LLVM Sim, another LLVM-based basic block throughput predictor that uses parameters from LLVM's instruction scheduling model. LLVM Sim has an entirely different simulation model than LLVM MCA. Despite this, applying DiffTune as is to learn LLVM Sim's parameters has the same results, not only matching but actually lowering LLVM Sim's error compared to that of the default parameters. I also just want to note here that we're only including the error for Haswell because LLVM Sim only has default parameters defined for the Haswell microarchitecture. So, DiffTune can learn all of LLVM MCA and LLVM Sim's parameters, leading both to have lower error than when instantiated with the default parameters. So what do these learned parameters look like? So I'm going to walk you through two case studies here of the learned parameters. So for simplicity, these case studies are from a run of DiffTune where we just learn only the write latency parameter, and we leave all other parameters as their default. So first, let's consider this basic block with an XOR. Because this XOR is a zero idiom, which sets the value of the R13 register to 0, the ground truth timing of it when ran for 100 iterations is 31 cycles. So although XOR usually forms a dependency chain with itself and would therefore take somewhat longer to execute, many x86 CPUs recognize that this specific usage breaks the dependency chain and they execute this basic block faster. The version of LLVM MCA that we're working with doesn't recognize zero idioms. So with the default write latency of 1 in LLVM MCA, LLVM MCA predicts that this basic block has a timing of 100 cycles, since LLVM MCA believes that XORs form a dependency chain, and the write latency of 1 means that it takes 1 cycle for each XOR to execute. Most of the usages of XOR in DiffTune's training dataset are actually zero idioms, though. So DiffTune learns a way around the lack of the zero idiom detection by instead learning a write latency of 0, meaning that instructions dependent on an XOR don't actually have to wait for that XOR to finish executing before they dispatch. And so this isn't always correct for all types of XORs, but it does allow LLVM MCA to make more accurate predictions in the very common case of using an XOR as a zero idiom. Unfortunately, these types of modeling bugs can also lead DiffTune astray. So for instance, consider this basic block, which is a single self-dependent instruction with a latency of 6 cycles, leading to a ground truth timing over 100 repetitions of about 600 cycles. LLVM MCA doesn't detect the self-dependency through memory in this basic block, instead assuming that no memory accesses can alias. This means that even with the default write latency of 7 cycles in LLVM MCA, the default prediction is 109 cycles to execute this basic block 100 times. Instead, DiffTune learns a write latency of 62 cycles here, a value that's clearly semantically wrong, but it does lead LLVM MCA to have slightly more accurate predictions. So this is something of a downside of learning values through just minimally constrained optimization. So any values that lead LLVM MCA to be more accurate are accepted by DiffTune, even if the values don't correspond to semantically reasonable values. So in conclusion, we present DiffTune, a programming tuning algorithm and implementation that learns a differentiable surrogate of a given non-differentiable program, and then optimizes the program's parameters using gradient descent through the differentiable surrogate. Given a microarchitecture-independent simulator sketch, like LLVM MCA, DiffTune can learn all of its parameters to equivalent or better accuracy as the hand-tuned defaults. So what does this all add up to? Well, so we know that we can use DiffTune to tune parameters of CPU simulators, like LLVM MCA and LLVM Sim. But we hope that DiffTune generalizes beyond just this domain. So specifically, we hope to be able to use DiffTune to tune parameters of arbitrary programs, including massive scale programs with large numbers of parameters, ideally being able to simplify the task of program tuning down to just gathering input-output examples for any given problem. So thanks for watching, and if you're interested, please check out the full version of the DiffTune paper. Thank you.